Here are some additional differential equations that we will solve. Okay, going to separate the variables. Going to integrate both sides. On the left, because of the negative, I'll have a negative natural log, absolute value, equals 7x plus c. Get rid of the negative. Exponentiate both sides. Get rid of the absolute value, c star. Solve for y. Let's see, that's 3 minus c star e to the negative 7x. Plug in my condition. And conclude that c star equals 2. And finally write the particular solution, which is 3 minus 2 times e to the negative 7x. Example number 2, I'm going to start by rewriting this in a way that makes separation a little easier. So 3x to the 1/2 times y to the 1/2. Separate the variables. dy over y to the 1/2 equals 3x to the 1/2 dx. I will integrate both sides. And this one, we've got to be careful, it's not natural log, it's y to the negative 1/2 power dy equals 3x to the 1/2 dx, the integral of that. So my integration now is going to be y to the power of 1/2 times 2 equals 3x to the 3/2 times 2/3, so these will cancel out, plus c. Let me just rewrite that. 2y to the 1/2 equals 2x to the 3/2 plus c. I'm going to do something a little bit different here, which is different from the other examples. I want to show you that you can solve for c at different points along the way. If I solve for c now, this is prior to getting y by itself, I can say that 2 times the square root of 256 equals 2 times 4 to the 3/2 power plus c. If I solve for c in this case, c will come out to be 16. So then I have 2y to the 1/2 equals 2x to the 3/2 plus 16. Now I'll solve for y. I'll divide everything by 2. Y to the 1/2 equals x to the 3/2 plus 8. Now I'll square both sides. So y equals, now I'm squaring both sides, not just part of the side, the whole side. And that becomes the solution to the differential equation. But I want to come over and talk about the original way we did it to show you how they are eventually the same. If I solve for y first, then I have y to the 1/2 power equals x to the 3/2 power plus a new c. Now we're going to get y by itself, so I'm going to square both sides. So y equals, and I'm going to square the entire side over here. This is how we've done the other examples where we first solved for y. Now I'm going to plug in my condition. So now I have 256 equals quantity 4 to the 3/2 power plus c squared. I'd have to square both sides, and ultimately I would solve for c. In this case, c came out to be 8. And if I plug this back into here, which is where I started to solve for c, then I get y equals x to the 3/2 power plus 8 squared, which is the same exact answer that I got before when I solved for c at a different point. The point that I am trying to make, that c was equal to 16 here, c was equal to 8 here, but ultimately when I solve for y in the final stages, the answer should come out to be the same, and the c's get accounted for with some of the algebra. Example number 3. This one is similar to one of the ones we did before in the fact that there is no x in the problem, only a dx, but not to worry. So dy over the cosine squared y equals 1 dx. Integrate both sides. Now, in order to integrate this left-hand side, it looks like we will be better off writing it as secant squared y instead of 1 over cosine squared dy, so that we can employ our book of memories. So this becomes the tangent of y equals simply x plus c. I'm going to show, like I did in the last example, that you can solve for c at various stages of the problem. In this particular method, I'm going to solve for c now. So the tangent of 0 equals x, which is 0, plus c. And I conclude from here that c equals 0. Continuing from there, then I have the tangent of y equals x. Now I've got to solve for y, getting it by itself. So y equals the inverse tangent of x to be my solution to the differential equation. If I do it the alternate method, which is the method I actually prefer, is I like getting y by itself first. So then I have y equals the inverse tangent of x plus c. Now I'll use the condition 0 equals inverse tangent of 0 plus c, and we can conclude from that that c has to equal 0. It just so happens that c came out to be 0 again, and so y equals the inverse tangent of x, which is consistent with this. Check, check. Just in case you are wondering, suppose you were looking at the function that we found here, y is the inverse tangent of x, and you say, wait a minute, I know that dy dx is supposed to be 1 over 1 plus x squared, which then says, wait just a second. How come this says that dy dx is the cosine squared of y? If you recall, in the development of this original derivative, we said the tangent of y equals x, or x over 1. Then we drew a right triangle. This was the angle y. The ratio for the tangent was opposite over adjacent. Then we found the missing side, which was 1 plus x squared under the radical. Then we did our implicit differentiation and said secant squared y dy dx is equal to 1. From there, we said that dy dx was equal to 1 over the secant squared of y. And then we also said, well, 1 over secant squared of y is the same thing as cosine squared of y. So there we have it. Dy dx is equal to the cosine squared of y. If I wanted it as a function of x, then I come over and say 1 over the square root of 1 plus x squared, but square the whole thing, which is 1 over 1 plus x squared. So the truth is dy dx is both equal to this as a function of x and to this as a function of y. Final example. Okay, I'm going to separate the variables. Dy over square root of y equals 4 natural log of x over x dx. I'm going to integrate y to the negative 1/2 dy equals the integral for natural log of x over x dx. The left hand side, y to the power of 1/2 divided by 1/2 or times 2 equals, okay, this is a little bit trickier in that this one is not a simple antiderivative. It requires a u substitution. If I let u equal the natural log of x, then du is 1 over x dx, and then dx is x times du, which yields this integral. Alright, so we have 2y to the 1/2 equals 4 u squared over 2, which reduces to 2u squared plus c. So let's come on over here, and we have 2y to the 1/2 equals 2. I'll back sub in for x now. Here we go. Choices, choices, choices. When do you want to solve for c? That really is your choice. But I'm going to do it where I solve for y first. So y to the 1/2 equals the natural log of x quantity squared plus c. Then I have to square both sides, so y equals the natural log of x squared plus c. That quantity gets squared. I'll plug in y, for 4 for y, and I'll plug in e for x. So the natural log of e is 1 squared plus c squared. 2 equals 1 plus c, and therefore c equals 1. So my final answer, my particular equation, the natural log of x squared plus 1.